Okay, so in this video, we'll talk about elemental dipole antennas, kind of an introduction, a super basic, simple introduction to it. So why are we even talking about elemental dipole antennas? From what we've talked about so far, now, the last paragraph we read in the last video about this in that for a complex antenna shape, stop there. A complex what? Antenna. Now, antennas in real life can be what? Complex. But first things to antenna, okay? Once you hear antenna, what should come to your mind is something that can what? Receive or send electromagnetic wave, okay? EM wave, okay? Of course, we've talked about JS being the source current, okay? So now that's for antenna. Then when you hear this thing, elemental, this is kind of the main thing we are talking about in this video, elemental. Okay, so since antennas can be complex, how can we analyze or go through or talk about or understand or even discuss or get expressions, equations for something that's complex? So forget about the complexity. Okay, forget about the what? Complexity. Let's go to the basic. Simple antennas, elemental antennas. Okay? Simple antennas, elemental antennas. And so when we talk about elemental antennas, we're just talking about antennas that are simple. So we have a lot of assumptions and they kind of give us the idea of an ideal antenna. So the real life things, real life factors will kind of leave out some of those things, based on assumption. All right. Now, then dipole. Oh, I've not talked about this. Dipole just mean it has two blades. Should I use the word blade? Or let's just say two parts, okay, with opposite polarity. We are dealing with AC. We are dealing with AC, right? That's the kind of current we are working with. So we have the kind of antenna we're talking about now are antennas with what? Two parts. So with opposite polarity. Of course, AC, alternating currents. So, meaning at some time, here will be positive, here will be negative. Then at other times, here will be negative and here will be what? Positive. But the point is, we have two parts or two blades to reach to this kind of antenna. And the both of them have opposite polarities. So, basic antennas, elemental with opposite parts, two parts with opposite uh, polarities, antennas, elemental dipole antennas. Okay, so now look at this. Given the complexities, like I said, okay, some minutes ago, given the complexities of antennas as mentioned in the beginning of this section, exact solution for most antenna structure have not been obtained. Are you kidding? Can you imagine that? So, so look at it. Don't even bother yourself trying to go for this complex one yet. So, solutions generally rely on what? Certain approximation, like I talked about. Those approximation will now lead to the idea of ideal antenna. Okay? So, which may not even exist. Okay, so solutions generally rely on certain approximation. Approximation. Such as what? Sorry about that. Okay. Assuming what? Assuming the form of the current distribution over the antenna surface. Current distribution, we're talking about this guy, okay? The source current, okay? So the form of this guy, how is this guy distributed over the surface of the antenna? Okay? So that's what, such as we assume the form of the current distribution. Of course, in real life, we don't know the form yet. So we are assuming it. We assume so that we can solve. We assume so that we can get an approximate expression for the antenna, how it works, the transmission and receiver and things like that. Okay, so this is one of the assumption. Okay, the current distribution over the antenna surface. But even with this assumption, the problem of computing the field of the antenna remains a difficult one to solve. Can you imagine? Imagine say we don't assume before. So as a further simplification, that's trying to make this easier, the solution is what? Typically restricted to field ideal antennas. The electric, I talk about ideal, right? Talk about ideal. So yeah, the solution is typically restricted to field ideal antennas. The electric and magnetic dipoles, so it's restricted to field antennas, and we are talking about what? The electric and magnetic what? Dipoles. Okay, so for these antennas, we may obtain exact solution for the field. Antennas where we assume JS, okay, that's the current distribution over the surface of the antenna. When we assume that, and then also we now do what? Restrict our calculation to what? Ideal what? Antennas for what? The electric and what's the magnetic field. All right, so ideal ones. So meaning we are not considering, most things we'll be dealing with are just what? Free space, you see, mu naught, beta naught, all those are free space. Free space meaning all those other factors that will affect electromagnetic wave as it propagates through space. Those things that will affect them, we are not even considering those things now. Okay? Things that will affect electromagnetic wave as it travels through space. Those things, other factors, those other things in space that will affect them, we are not even considering them. That's why most of our equations here, we have what? Naught. That's a mu naught, beta naught. There's another naught. Okay, we do not have any other naught, but we still have some naughts. If you see epsilon is also naught, all right? But do not worry about the knots. Just know that the knots. all right, where are we? Yay. Okay, so here we are. So for such antennas, for these antennas, we may obtain exact solution for the fields. Good. These solutions provide considerable insight into the behavior of other more realistic antennas for which exact solution have not been obtained. That is to say, when we have a solution for this our ideal antenna, which we've made many assumption and approximation, or we've made some assumption and approximation. So we now have the antenna we are working with. After all those assumption and approximation, we can refer to them as ideal antennas. When we get a solution for that kind of antenna, we can use that solution. Okay, this solution provide considerable insight. We can now use that solution to consider or have insight about the behavior of other more realistic antennas. Okay, that's all for this video. In the next video, we'll talk about these other guys, which is what? Electric dipole. Remember, we talked about what? We say we assume JS, right? We assume JS, and they will now work with what? Approximate or ideal this one and ideal of this one. Okay, so this one is considered done, like we have it already because we assume it. So what are we searching for? What are we now deriving expressions for? This and this. So electric dipole. And if you open to the notes further, you will see magnetic dipole somewhere. That's one for electric dipole. Yeah, magnetic dipole. Okay, yeah. So that'll be all for this video. Thanks for watching. Like, share, subscribe, comment. Click on notification bell when you subscribe so you will see the videos immediately they are posted. Thanks for watching. See you in the next video. Bye for now.